So I'm Donna Nelson. This is Chemistry 3053, and today we're going to start Chapter 12, Alcohols and Phenols. And let's look at what we're going to cover. First, structure and properties of alcohols, acidity of alcohols and phenols, preparation of alcohols, the substitution or addition. Some of this will be review. And then we'll have 3 additional videos to cover the remainder of Chapter 12. So let's start. Alcohols possess a hydroxyl group. You can see this is ethanol, cyclopentanol as examples. Hydroxyl groups are extremely common in natural compounds. You can see that, so this is an insect pheromone. And you can see that this is an antibiotic, which is a diol. You have 2 hydroxyl groups in it. Here are more cholesterol and vitamin D3. And this is an example of a perfume, which contains an alcohol functionality. Phenols also are a specific class of alcohol. It's an aromatic compound that possesses a hydroxyl group. Examples, naturally occurring examples of that are dopamine, urushiol, present in the leaves of poison ivy and poison oak, capsaicin, you can see, and also THC. So alcohols are very prevalent in nature. Now let's look at the alcohol nomenclature. They're named using the same procedures that you've seen before. So most of this is going to be familiar to you. First, identify the parent chain. As always, here it must include the carbon that the hydroxyl group is attached to, and this is assuming that the hydroxyl group is the highest priority functional group present. So you identify and name the substituents. You assign a locant to each substituent. Give the carbon that the hydroxyl group is attached to the lowest number possible. You list the numbered substituent before the parent name in alphabetical order, as you have done before. You ignore prefixes except iso and di, tri, tetra, etc., and neo, as you've seen before. So most of this is review. The OH locant, the number that tells its location, is placed either just before the parent name or just before the alcohol suffix, the OL suffix. And that's going to depend on how many functional groups are present in the molecule. You'll see an example. Not on this slide, but the next one. So here we identify the parent chain. So it's 5 carbons. So this is pentanol. The E is replaced with OL. Here you can see, once again, you use the longest chain as the parent chain, except if you have a hydroxyl group, the chain must contain must bear the hydroxyl group. So here you would not use the 8-membered alkyl chain. You would use the 6-membered alkyl chain, 6-carbon alkyl chain. So this is a hexanol because the alkyl chain that bears the hydroxyl group contains 6 carbons only. Now you assign a locant and prefix to each substituent. So let's look at this. This is a good example to consider. So you can see that this has 1, 2, 3, 4, 5, 6, 7. This is the same molecule redrawn. Count it the other way, so it's 7 carbons in the longest chain. And this is therefore a hept heptenol. Remember, the highest priority group goes at the end of the name, so heptenol. And furthermore, this is a trimethyl heptenol. And so this one is the correct numbering system, not the one on the right. The one on the left is correct because in this numbering, the alcohol functionality, which is the highest priority functional group, is given the lower number. So it is, this is, and then the other groups, functional groups or substituents, have numbers accordingly with this system on the left. So therefore, this is a trimethyl heptenol, and when you add in the numbers, it is a 5,5,6 trimethyl hept-6-ene-2-ol. Okay, and so it would not, you would not be able to name this as a 2-heptenol because you're going to have to specify where both the double bond is and the hydroxyl group is. So in this one, you only have one functional group. It is a pentanol, and so this can be named correctly as either 3-pentanol or pentan-3-ol. So the 3 can come at the beginning or the end of the stem because you only have one functional group. So there's no ambiguity as there would have been on the previous slide. So for cyclic alcohols, the hydroxyl group is always at C1. And again, that is assuming that the alcohol functionality is the highest priority functional group. So this is cyclopentanol. It doesn't have to be numbered here because you only have one substituent or functional group attached. Over here now you have to number it because you've got some other groups attached, and in order to specify their location, they have to be numbered, they have to be specified relative to the hydroxyl group. So you start numbering at the hydroxyl group 1, 2, 3. So this is going to be a 3,3-dimethyl cyclopentanol, and you don't have to specify that the hydroxyl group is at the 1 position because that's understood. And so you don't have to put the 1 in any place. The hydroxyl is understood to be at C1. And when you examine and figure out the configuration of this carbon, you'll see this is the highest priority group. Next, next. So it's counterclockwise, except you have the hydroxyl group going back. So when you flip the molecule over so that the CH will be going back, this is going to be an R configuration. Common names for some alcohols are also frequently used. So 2-propanol is isopropyl alcohol. 2-methyl-2-propanol is tert-butanol. And phenylmethanol is benzyl alcohol. So you'll need to learn both of the names in those cases. Also, alcohols will have substituents at the alpha carbon. That's the carbon bearing the hydroxyl group. If you have one alkyl group, it's a primary alcohol. If you have 2 alkyl groups on the alpha carbon, it's secondary. And if you have 3 on the alpha carbon, it's tertiary, just as with alkyl halides. When a hydroxyl group is attached to a benzene ring, the parent name is phenol. So this is phenol, and you'll need to learn that. So once again, remember that when the hydroxyl group is the highest priority functional group, it is understood to be at C1. And so over here it is at C1, and so the other substituents are numbered, their positions are numbered relative to the hydroxyl because it's the highest priority group. So this will be 1, 2, 3, 4. And then putting these in alphabetical order: 4-chloro, 2-nitro, phenol. Commercially important alcohols. Methanol is the simplest alcohol. Obviously, it has 1 carbon with a suitable catalyst. 2 billion gallons of methanol is made from carbon dioxide and hydrogen every year. Methanol is poisonous with many uses: a solvent, a precursor for chemical syntheses, and a fuel. Ethanol is also commercially important. It's produced by fermentation of grains or fruits. Industrial ethanol is made via acid-catalyzed hydration of ethylene, 5 billion gallons per year in the U.S. alone. Ethanol has many uses: solvent, a precursor for chemical syntheses or fuel. And here, in these cases, it's denatured. Usually a little bit of benzene will be added to it to spoil the taste. And then also human consumption. Ethanol is suitable for drinking, and in those cases, it is heavily taxed. Isopropanol, rubbing alcohol. Isopropanol is made industrially from the acid-catalyzed hydration of propylene. It's poisonous, but it has many uses as an industrial solvent, as an antiseptic, and as a gasoline additive. So now let's look at the physical properties of alcohols. The hydroxyl group of an alcohol has a huge effect on its physical properties. Solvation and boiling points, for example. Here, ethane is minus 89. Chloroethane is 12 centigrade. Ethanol is 78 centigrade. The comparison between chloroethane and ethanol is interesting because these two have very similar molecular weights. And remember, molecules that have molecular weights that are close often have similar boiling points. And as you increase the molecular weight, generally, you increase the boiling point. And so chloroethane is going to have a greater molecular weight than ethanol, but yet ethanol's boiling point is higher, and much higher. And it is higher because ethanol is capable of hydrogen bonding, and chloroethane is not, as you recall. The physical properties: alcohols with 3 carbons or less are miscible in water. The hydrophilic region dominates the molecule, but when you have more than a much longer hydrophobic chain, then the solvation starts to drop off. What is happening up here is the hydrophilic region. When this comes in contact with water, it literally drags the hydrophobic region of the molecule into the water. But here, if the hydrophobic region if that chain is so much longer, it becomes more and more difficult for the hydroxyl group to drag it into water. And the impact starts to increase quite a bit at about 6 carbons. And that is the case whether you have an alcohol or a carbonyl, whatever functional group you have. The solvation begins to drop off around 6, 7, 8 carbons. So here, physical properties of alcohols. The physical properties are going to be determined by both the hydrophobic and the hydrophilic region. The alcohol needs some water solubility to travel through aqueous media and to behave as the antibacterial agent. So the alcohol needs some water solubility that will be provided by the hydroxyl group. It also needs a significant hydrophobic region in order to penetrate the microbial membranes. And so you can see as the alkyl chain length increases, its potency increases. And then as the miscibility with water decreases, its potency is going to decrease. Physical properties of alcohols. So this one, hexyl resorcinol, is used as an antibacterial and an antifungal agent. It has a good combination of hydrophilic and hydrophobic regions. Now, acidity of alcohols and phenols. Some of this you've already seen. You need a strong base like hydride to deprotonate an alcohol and generate an ethoxide. This is also a very strong base, but not as strong as the hydride. And here, hydrogen gas is evolved, so that will drive this to completion. And it's also very nice because you don't have any impurities to remove. The same situation with sodium, potassium, or lithium metal. Here, this will be used to convert the alcohol to alkoxide, and once again, hydrogen gas is evolved. Now, the alkoxide, remember that as it's a conjugate base of an alcohol, and as a comparison, compare it to the alkyl anion, the amide, the oxide, and the halide. So let's look at these. Remember that this is the most, of these four, this is the most stable of these anions. Alkoxide falls up here, not that close to halide, and then you have the amide, which is a much stronger base, and then the alkyl anion, which is an exceedingly strong base. Remember that alkanes have a pKa between 45 and 50, and that's why this is going to be the strongest base, because the corresponding acid has the greatest pKa. And then amide, the pKa is between 35 and 40. Here, the alcohol has a pKa between 15 and 18, and the halides are between 3 and minus 10. So in each case, you can see that as the anion is stabilized, the acidity of its conjugate acid increases. So there are the two trends. Remember the REO, to rationalize the relative acidities between the alcohol and these other compounds. Remember REO, it's atom, resonance, induction, and orbital. And so these things can be, it's necessary to consider them all when you're comparing alcohols to other molecules. But it's not necessary to consider all of those factors when you're trying to decide among alcohols. So here, if we're just comparing two alcohols. So each of these, you have a hydroxyl group. So in recalling REO, the first part of REO, the A is the atom upon which the negative charge will reside. And here it's going to be oxygen in each case. So you don't need the entire REO. You don't need to consider all of the items inside REO to compare these. And also, remember the O of REO. The O is for orbital. Well, in this case, the negative charge is going to reside in the same type of orbital. So you don't need to consider all of these factors. Here we'll just consider things like resonance and induction when you're comparing alcohols, the relative acidities of two different alcohols. So in this case, resonance is important. Resonance is important. Cyclohexanol, you have no resonance. Phenol, you have 5 different resonance structures where you're moving the negative charge around the different atoms. And then here you have the 2 resonance structures of the benzene ring. Now, in this case, you have ethanol and trichloroethanol. So this is the induction, the I of REO. And here, this one is going to be much more acidic because when the negative charge is generated on oxygen, it will be stabilized by the electron withdrawing effects of the 3 chlorine substituents. And so withdrawing the electron density off of oxygen spreads the electron density out and stabilizes, it will stabilize that anion. So each of these chlorine atoms will bear a little bit of a partial negative charge. So the negative charge will be spread out and you'll actually be able to see the chlorines become partially negative, bearing a partial negative charge. And so therefore, this molecule, the trichloroethanol, is more acidic and it's reflected in a lower pKa. Solvation effects. Now remember, if you remember, back when we were considering the nucleophilicity and the stabilities of the anions, I told you at that time to consider the REO effects, and also you had to consider polarizability, steric effects, and solvent effects. Now here, you're saying solvation effects. That's not quite the same as solvent effects. Solvent effects would be switching from one solvent to another, switching from a polar protic solvent to an polar aprotic solvent, changing solvents. Here, this is a comparison that's made in the same solvent. Okay, so this is called solvation effects. And here, this is the solvation effects are actually, that one observes here, that's actually due to a steric effect. The anion that is formed from this butanol is much more sterically hindered. The butoxide is much more sterically hindered than the oxygen atom bearing the negative charge in ethoxide. And so what happens is, since this one is much more sterically hindered, solvent cannot crowd around the negative charge in order to stabilize it. But over here, there's not so much steric hindrance, and so it is possible for the solvent to crowd around O- and stabilize it. And so that's why ethanol is a little bit more acidic. And here, so that's called solvation effects. It's really not solvent effects because you're not changing the solvent. Both of these are in the same solvent. And this is a drawing that, a figure that shows what I just said. So here you have the T-butoxide. This is O- right here, and you can see it's much more difficult for solvent molecules to get in there and crowd around O-. But here, it's much less blocked. So you can see there's more solvent molecules can get up close to O- in ethoxide and stabilize it. And what happens is these solvent molecules will actually become polarized, partially positive, partially negative. And that stabilizes O- because that's spreading the negative charge out. The preparation of alcohols. that they can be synthesized from alkyl halides, as you have already seen. So you've seen it in the SN2 reaction. OH comes in, does a backside attack. You've seen it in the SN1 reaction, where chloride departs and forms the T-butyl cation, and then oxygen attacks the tertiary cation, not T-butyl, the tertiary cation, and then oxygen attacks the tertiary cation, and you have the SN1 reaction. So this is a review. You have already seen this. Preparation from an alcohol by those two mechanisms. Preparation of an alcohol from an alkyl halide by those two mechanisms. Now you can have preparation of alcohols from alkenes by these addition reactions, and these are also reviews. You saw this in Chapter 9, Sections 4, 5, and 6. You remember you can use a little bit of acid and water. So here when it says dilute acid, that means in water. And so you're going to get the acid-catalyzed addition of water across the double bond. Here, remember, this is oxymercuration, and oxymercuration also gives you the Markovnikov addition. Both of these are Markovnikov addition. When you're going through the cation, as this one does, because the first step in the top mechanism is going to be protonation to give you the cation. Using this, it's possible to get rearrangement in some reactions, not this reaction, obviously, but remember oxymercuration, you get the same product, but no possibility of rearrangement of the carbon skeleton. And with hydroboration, remember you get the anti-Markovnikov addition without any rearrangement. So that's a nice little review of the preparation of alcohols from alkenes. And so we'll stop here and continue on with the chapter in the next video.